In this video, we're going to continue on with section 1.1, which is solving linear equations, but in this section, we're going to talk about situations where you don't have a linear equation to begin the problem. Okay, so sometimes you're going to have equations such as the example that you see here, where after you distribute through or FOIL, you're going to have some y squared terms running around, or you may have multiple things in the denominator, or situations that aren't as easy to solve. In that case, you're going to have to use the skills that we've built up so far in this course to get it into the form of a linear equation. Okay, and so that's what we're going to practice here. So let's look at two examples to start off. And so if you look at the left, we'll start with this equation. You see that we have differing denominators, and so as usual, as we practice in section R.7, we're going to have to find a common denominator in order to do the addition operation, so on and so forth. So to do such a thing, we need to look for the least common multiple in the denominator, and it turns out that it is this, x minus 1 times x minus 2. So I need to multiply this left-hand side by x minus 1 divided by x minus 1. This middle equation I need to multiply by x minus 2 over x minus 2. Okay, and I don't need to do anything to this 7 over blah, because it already is the least common multiple in the denominator. And so when I put everything together, I get a common denominator. And I'll just write that out here. Now that I have a common denominator on the right side, I can combine like terms. Okay, and on the left side, I can distribute through the top. Let's get 3x minus 3 over x minus 1, x minus 2. Okay, and then on the right side, I'm going to get x plus 5 over x minus 1, x minus 2. Okay, I have denominators that have x's in them, or really I've common denominators on both sides. So when I multiply both sides by the common denominator, okay, which is a valid move to do, so I'm multiplying both sides not by 1 but by the common denominator. And I can do that because I'm multiplying both sides of the equation by the same thing. What happens is that both of the denominators cancel out, and I'm left with 3x minus 3 is equal to x plus 5. Okay, I want to get the x's, all of the terms that have x in them, on the left, numbers on the right. So I add 3 and subtract x. What I get is 2x equals 8, okay, 5 plus 3, 8, and so x is equal to 4. X is equal to 4. Let's see if that works out. Okay, so let me substitute 4 into the original equation up above, and so I get 3 over 4 minus 2 is 2 equals 1 over 3, 1 over 4 minus 1, plus 7 over 4 minus 1 is 3, and 4 minus 2 is 2. 3 times 2 is 6. Okay, so is 3 halves equal to 1/3 plus 7/6? Again, we need a common denominator here, and the common denominator is 6. So if I multiply this by 3 over 3, I'm going to get 9/6 equals, multiply this by 2 over 2, 9/6 is equal to 2/6 plus 7/6. Does that work? 2 plus 7 is 9, and so yes, it does work out. Okay, so the left side, left equation, everything works out. The solution is 4 for real. Now let's look at the right. So I have 3x divided by x minus 1 plus 2 equals 3 over x minus 1. So again, I have denominators here, and I need to find a common denominator. And that common denominator is x minus 1. So I have 3x over x minus 1. And then I just need to multiply 2 by x minus 1 over x minus 1 to get me 2 times the quantity x minus 1 over x minus 1 equals 3 over x minus 1. Okay, so if I use the distributive rule to get 2x minus 2 there, I have 3x plus 2x minus 2 is equal to 3 over, what I've done on this right side is I combined these two into one term with x minus 1 in the denominator, and then over here x minus 1 in the denominator. Okay, I can multiply both sides by x minus 1, and that gets rid of both denominators. What I'm left with is 3x plus 2x minus 2 is equal to 3. Okay, I can add 2 to both sides, and then combine like terms. That gets me 5x equals 5, which in turn gives me x equals 1. Okay, so there's my possible solution. Now let's check it. Okay, so I substitute, so here's my sort of checking part. I substitute x equals 1 into the equation, and I get 3 times 1 is 3. 3 over 1 minus 1 is 0, plus 2 is equal to 3 over 0. Does anyone see a problem here? Hopefully you should, because if you'll remember, you cannot divide by 0. Okay, that's not a valid. Well, it may be a valid thing to do, but when you divide by 0, bad things happen. Okay, so it turns out that 1 is not a solution. So actually, there are no solutions here. No solutions. This doesn't check out, okay? And if it doesn't check out, then this is not a solution, okay? So x equals 1 is not a solution. Okay? In fact, there are no solutions to this equation. Okay, so now I want you to do another your turn here, where you have to turn this into a linear equation using the same things that I have done, and then solve for x. Okay. Now we're going to go on here to the last little bit and talk about applications of linear equations. You see linear equations, or they exist all around you, whether you see them or not. So they're in tons of real world situations. Okay? One of the most common ones is the linear equation that converts temperatures from Fahrenheit to Celsius. Okay? Fahrenheit to Celsius. And so here is that. Here is one way of the equation, from Fahrenheit to Celsius. Okay, you put Fahrenheit in, and then you'll get Celsius out. And then I want you to turn the equation from in terms of Fahrenheit, which it is now, to in terms of Celsius, which means you'd have F equals something. Okay, so I want you to pause the video and do that for a second, and then I will do it here in just a second. Okay, so hopefully you've paused the video and tried it on your own. I just want to solve for F here. Okay, solve for F. And so to do that, I'm going to rewrite the equation down here. 5/9 F minus 32. Okay. To get F alone, I need to first multiply both sides by 9/5. And so I get 9/5 Celsius equals F minus 32. And so to solve for F, I add 32 to both sides, and I get F is equal to 9/5 Celsius plus 32. Okay, so there's the same formula, but going from Celsius to Fahrenheit instead of Fahrenheit to Celsius. Okay, a simple application there, and just some practice rewording equations. Now, what you're going to most often have to do is I'm going to give you a word problem. Okay, so these are the dreaded word problems. I'm going to give you a word problem. You're going to convert it into mathematical form and then solve. So here we go. A total of $18,000 is invested by someone, okay, some in stocks and some in bonds. If the amount invested in bonds is half the amount invested in stocks, how much is invested in each category? Okay, so we need to turn this into mathematical form. Okay, turn this into mathematical form. So I'm eventually going to need an equation, and we know, since we're in the linear equations section, that it's going to be a linear equation. Okay, on the left-hand side of that equation is going to be the total invested. Okay, we don't know how much is in stocks and in bonds. That's going to be our x value. Okay, that's going to be the variable that we don't know. So, but I do know how much is total, and so I'm going to put 18,000 on the left side. Okay, 18,000 on the left side. And then the tricky part is, how do we write the right side? Okay, so first we should really define, we'll use x because x is the most common. Okay, we need to define what x is. And that's really going to come from the second example here, or the second sentence. If the amount invested in bonds is half of the amount invested in stocks, how much is invested in each category? So I'm going to call the amount invested in stocks X. Okay, and then the amount invested in bonds is going to be a sort of function of stocks. Okay, we know that the most basic form of this is that 18,000 invested, some is in stocks and some is in bonds. So it's basically 18,000 equals bonds plus stocks. Okay, we just need to now fit this x in there. Okay, so as I defined here, and I'll move down to a new line, I'm going to invest X amount in stocks. Okay, and then the second sentence says the amount invested in bonds is half the amount invested in stocks. So how do I write that? It's half the amount invested in stocks, so that is x over 2, okay, or half of x. And then I add them together. Okay, so I have 18,000 equals bonds plus stocks. Stocks is X, and bonds we know is half of X. So then we can add this together, and we get 18,000 equals X over 2 plus X. Okay, I can create a common denominator by multiplying the top and the bottom by 2 over here. And so there I get 2x plus 2x over 2 plus x over 2. That gives me 3x over 2. Okay. I can multiply both sides by 2 to get rid of the denominator. I get 3x is equal to 18,000 times 2 is 36,000. And then when you divide by 3 on both sides, you get that x is equal to 12,000. Okay? So that is the solution to the equation. Okay, x equals 12,000. And you can, if you want, go back up here before I multiplied by 2 there. So if I take that away, plug 12,000, or sorry, substitute 12,000 in to this original form, and you should get 18,000 out. Okay, and so there was 12,000, and remember X is amount invested in stocks, which means that there was 6,000 invested in bonds. 12,000 in stocks, $6,000 invested in bonds. Okay, so that's an application problem. So I'll include a second one here because these are often tricky. Okay, and so I want to give you as many examples as I can. So I promise I won't make this video too long. And I'll try to go through quickly here. So Shannon grosses $928 in 1 week by working 52 hours. Her employer pays time and a half for all hours worked in excess of 40 hours. With this information, determine Shannon's hourly wage. Okay, so again, I'm going to have left side and right side of this equation. Okay. The right side is going to be the total money made. Okay, so usually if there's like a money question, the total will be available to you, and you'll put that on the left side, 928. Okay, and then X in this question is going to be the number of hours, or sorry, it's not the number of hours worked. I'm looking for the hourly wage. Okay? The hourly wage. So, I know that she worked 52 hours, okay? And the interesting part is that she gets paid time and a half for all hours worked over 40 hours. Okay? So we know for the first 40 hours, she got paid 40 times whatever her hourly rate was, or is, which is what we're trying to find. Okay? So 40 times X. Then she gets paid time and a half, which is like 1.5 times your hourly wage, okay, for all hours worked in excess of 40. So how many hours in excess of 40 did she work this week? She worked 12. So she worked 12 at 1.5 times X. Okay, so there's my equation. Now I just need to combine like terms and solve for X. Okay, so I have 928 is equal to 40X plus 12 times 1.5. Okay, so 12 times 1.5 is 18. Is 18. So I have 40x plus 18x. Okay, and so when I add like terms, I get 928 is equal to 58x. Okay, and let me pull up a calculator, because x is then 928 divided by 58. And I can't do that in my head. 928 divided by 58 is 16. Okay, so x is 16. Does that make sense? Okay, what is that saying? It's saying that Shannon earns $16 per hour, okay, in her job. You can go back again, substitute 16, or I want you to, I need you to, okay, substitute 16 back into the equation, see if it actually works out. Okay, I'm not going to do that now, but for your questions, when you do it, you do need to do that check. Okay, it's not optional; it's required. Okay, for good reason. We saw in the last set of not applications, but the last set of linear equations that we did. Sometimes the solution doesn't work out, and so you need to be aware of that. So here's your turn. Okay, a store sells refurbished iPhones that cost 12% less than the original price. If the new price of a refurbished iPhone is $572, what was the original price? Okay, so answer that, and then answer the question: how much is saved by purchasing that refurbished iPhone? Okay, so that's your turn, and that's the end of section 1.1.